of last time, which I shall now write on the back of. Let's see if this pencil is strong enough to come through. The other marvellous thing about a piece of paper is that we can cheat proving the laws. So let's have a good old data type. I'm going to change the next. Is this? Oh, well, not on the screen. Let's get on screen. That's very faint, isn't it?
Do you need? I've got some coloured pens if you want.
I don't want to use a whiteboard marker,
These
but
are,
if you've got a.
These aren't whiteboard markers. These
But
are
if they're
felt
just,
pens.
I'll just go with this. Got a purple pen from Stuart. Are we shooting?
Yep.
Yeah. Okay. So let's have. Sorry, we're. Is that legible?
Yeah, just as good as you get.
Let's have good old maybe in its Agda incarnation. And I like to call the constructors yes and no, rather than just and nothing. Okay, so maybe is often used to model the idea of a computation that might go wrong. Something in maybe X, if you're lucky, you'll get an X, but you might be unlucky. Did everybody see why that's how we're modeling that? That a value in maybe X is either yes, you get an X, or no, and you get none. Yeah? Okay. But you can also see that maybe takes a set, the actual type former maybe itself takes a set and gives us a set. So it's some kind of map sets to sets, and we ought to be thinking perhaps we've got half a functor here from the category of sets to the category of sets. So we've got a function from set to set. Maybe we can grow that into a functor from the category of sets to the category of sets. So let's figure out what we need to do for that. We're shooting for something which I'm going to call all caps, maybe, and it's going to be a functor from set to set. So we start with a function from set to set. Let's figure out what we need to supply. It's going to be a record, and there's going to be some bits and pieces. We've got to give the action on objects. Right. Now the problem here is that without Agda, I'm going to have to be Agda as well as me. Or maybe you can help me be Agda. What should the action on object be? I mean, what type is it going to have? Right. It's going to be a function from the objects of set to the objects of set. So that's just set arrow set, right? That's so what does it do? What does it do to the dots, as it were? It's going to do maybe. Okay. And now we need to figure out what it's going to do to the arrows. So I'm going to build that with a helper function, which is why I've left a gap, but let's see if we can figure out what its type ought to be. I'm going to call this lowercase m maybe. Right. What it's got to do is map an arrow between any two sets to the corresponding maybe sets. So that's going to be, if somebody gives us two sets, S and T for source and target, and somebody gives us a function from S to T, we better give back a function from maybe S to maybe T. That's what the rules are. So you can see we're doing maybe to the objects, that's to each of S and T. And now we have to explain how we would transport an arrow joining those two objects, S and T, to an arrow joining the two image objects, maybe S and maybe T. That's the kind of category talk about what we're trying to do, but let's think about it in terms of functional programming. We've got a function from S to T, and we've got some sort of process which, if we're lucky, will give us an S. Can we figure out how to give back a process, how to give back a T? Hi.
Is it working all right?
It's not working at all. The only thing that's going on, it's stuck in document camera mode. So I can't use and the selector is completely frozen.
Okay.
If we can, maybe it just needs a hard reset.
Yeah.
Well, let's figure out what we can do here. So we've got a function that we want to use, if you like, to post-process the result of our maybe S. If we succeed, let's figure out how to do it. We're going to have two cases. We've got a function in both cases. In one case we'll have yes, S, and in the other case we'll have no. So the idea is we post-process a successful result if we get one. But there's nothing we can do to recover from failure. So if our maybe input says no, what should we give as the output? No. There's nothing else to do. Sorry, that's to say, you are correct. The output should be no. If, on the other hand, our maybe S process succeeds and actually gives us an S, how about our maybe T process? We can, indeed, that can succeed, and we can give back f of s. So we've successfully built the operation that says, we know we'd like to do f afterwards, we're going to try and see if we get an s, and if we're lucky, we'll be able to turn that into a t. Do you remember the operation map on lists? Which was take a function, do it to all of the elements of a list. It had a very similar type to this. If you had a function from S to T, map would give you a function from list of S to list of T. Now we've got something which takes a function from S to T and gives you a function from maybe S to maybe T. So it's the same pattern. And all that's going on is we're saying, wherever you find an element of this source type S, use your function. So list packs up elements in one particular sort of a way, maybe packs up elements in another sort of a way, but the general plan of wherever you see an element, apply the function is still good. Yeah? You can see all that's going on with maybe is that it's expressing a particular way of packing up values some of the time. Yeah? So just following the pattern, we can build a function that we can build a higher order function that takes an operation on elements and does it to all the packed up elements wherever we find them. Okay, so, right. But that's behaving quite sensibly. I'm probably going to go with okay, well, I can keep going for a bit on paper and then switch back. Yeah, right. So we have two laws to check. Do that. The first law says, what happens if we choose this little f to be the identity function? Yeah? So what we're saying is, do the identity function to each element as you find it, leaving everything else as it was. What's going to happen? You'll get the same thing back. You can see, if we replace this f by the identity function, we'll just have the identity function applied to s, and our maybe operation will turn yes s into yes s and no into no. So it will indeed map the identity function on elements to the identity function on maybes. The other thing that we have to check is that if we do maybe twice with some function f and then some function g, that gives us the same thing as if we compose f and g first and then do maybe just once. Yeah? And that's going to come out the same as well. So I get to write, I'm going to write dot 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 here, because hopefully in a moment I'll be able to fill in the blanks with the computer. So yeah, one important source of functors, and this is pretty much the sort that you get in Haskell, is things that behave a bit like containers for elements. And the map. Sorry? Right, that's fine. So the map operation just says if you've got a function that acts on elements, lift it up to work on all the elements packed up inside some larger structure, and you keep the structure that surrounds the elements the same. You just act on the elements where they sit. So it's like, I always think of it as like a neutron bomb. We're always taught to be scared of, the neutron bomb is the ultimate in kind of capitalist destruction. It just sends sort of gamma radiation everywhere, killing everything that's alive, but leaving all of the infrastructure intact. So that's just like, you've got a function that turns people into corpses, and you map it across an entire city. And when you have a city full of people, you end up with a city full of corpses. So that's the idea. Surrounding structure survives, elements get acted on. So that's the idea. And one thing, it's always interesting to play, like how do you spot a functor? I mean, I look at this definition of maybe, and I think, yep, that's going to be a functor. What am I thinking? Right, cool. Yeah, I will do that. Yeah, no worries. These things happen. Thanks for sorting it out. So what's going on here? I'm looking at the way this X parameter gets used in this data type declaration, and I can see that some of the constructors pack up elements of X. So this X is used only to give some types of some fields, of some arguments to some constructors. And that means we've got something container-like, which means we're going to be able to write some sort of map-like operation. So you can look at the data type and immediately see that this is going to work out. And one thing I like to try to teach people is to get fed up with being made to work. So I'm saying you just need to look at this data type and you can see that there's going to be some kind of map operation. Why am I having to do the work to write this map operation? Why am I having to prove these laws that are always going to work out? Isn't that annoying? Well, yes, it is annoying. But at the moment, there's not a lot we can do about it. It's nice to see, reassuring as a source of exercises that they're going to be easy exercises. I can set exercises and I know they're going to work. You can say, oh, this is something which is going to work out. If we look at vectors, how does vector use its set parameter, its x? Well, in the cons constructor, it uses that set x to pack up an element, and then recursively, also in cons, it uses another vector type to pack up some more elements. So all we're doing is packing up elements. So we're going to get a map operation that works. Knowing one when you see one is a thing that will gradually happen. You should expect these other operations to show up. Let's see if we have technology. Electricity. And I think I'll give it a go with, well, I usually do use the HDMI connector, don't I? And let's see what happens if I do that. A whole pile of stuff appears. And then I actually want to switch this one off so I get a board. Right, I'm in the middle of writing the lecture 4 file. Let me just quickly flash up where we were. I guess I should make this a lot bigger and make the font bigger too. So we had a whole bunch of stuff. We were looking at functors, and I left you to do vec. We had adding things being a functor. Ooh, we'll come back to this stuff in a moment. And I ended up actually not needing any of that stuff, I don't think. Oh, yep, good. Right, there's a whole load of mess here. What I want to do I finished this construction off, but I had to do rather more intimidation than I would ever expect of any of you. But let me point out the interesting parts of the category of categories. So we had this idea that since functors are like arrows between categories. Maybe they join up like categories as well. So we have to give the identity functor, and all you can see is we have to say what it does on objects, the identity function, what it does on arrows, the identity function, and then prove some laws. How about composition of functors? All we do is compose the action on objects and compose the action on arrows. So the idea is that a functor packs up some kind of structural operation on objects and the way to transform the pictures and the way to transform the arrows simultaneously. So that means a functor gives you enough information to transform a picture. Right. So I've got pens. Right. Okay. So in particular, if you've got a picture where we've got an arrow here, F, and an arrow here, G, then we know the composition, F then G, has to exist. And we do some functor to this picture. We're going to get F of R.
Can you do it on the left?
Sorry?
To the left of the picture, the existing one?
Here?
Yeah.
Okay. We got F of R, F of T, F of S. We've transported our dots, and then we get F map G and F map of F then G. And we know the laws tell us that the identity arrows inside the dots get mapped to themselves, and that if we compose and then map, it's the same thing as mapping each of the pieces and composing them afterwards. So, what does the identity functor do to this picture?
The exact same.
Yeah, it's the exact same. We do nothing to all of the dots and nothing to all of the arrows, so we do nothing overall. And similarly, if we've got one functor F that turns this picture into this picture, and another functor G which does something similar, we could have made, we can compose the functors and do the journey in one step, rather than doing the journey in two hops. But the point is that instead of just thinking separately about how to do something to the dots and how to do something to the arrows, we think of it as one operation that transforms whole pictures by doing stuff to the dots and stuff to the arrows. It's quite abstract, but it becomes quite powerful. So I'm going to switch to this. This is just me hacking away. What I'll do is I'll grab a bunch of this stuff. I need to copy that.
Increase the font.
Yeah, I don't know what happened there. Oh, it's just per file. That's annoying. Paste, change file name. Right. So the first thing I've done in this file is just to grab myself the identity functor and composition from functors just by unpacking the category of categories. So I can open a structure inside a where clause if I want to grab at bits of it without kind of scattering it all over the floor. So all I'm saying is give me the identity functor from the category of categories, and give me the composition operator from the category of categories. But then you can see that I tell you no lies. Here's maybe. Here's this function that we just built. You can see the function gets done everywhere you see an element of x. Here, you do the function to it. And then I have to prove that I can, so I'm saying, here's the maybe functor from set to set. Action on objects is the maybe type constructor. Action on arrows is this thing that we just built. And then I have to prove some laws. And that's it done. Maybe I should do those more slowly so you can see what's going on. Let's at least look at the identity law. The other one's very, very similar. Right. So we get some ugly looking stuff. But you can see when we do control U, control C, control comma, to expand definitions as much as possible, we're just being asked to show that maybe applied to the identity function just gives you back the identity function. Now they don't have the same implementation. I should explain something about the word extensionality. Right. So the extension of something is its externally visible behavior, from the Latin for drawing out. So two functions are extensionally equal if they map equal inputs to equal outputs. So all you can do with a function is apply it. So what we're saying is, when you use it, it behaves the same. Yeah? Whereas they are intentionally equal if they actually have the same implementation, if what's inside the box is the same in both places. Now we know the identity function, lambda e arrow e, doesn't do any pattern matching and gives you back the input straight away. We can see that maybe of the identity function does do some pattern matching, but if we instantiate it, if we instantiate f with the identity function, then in each case we'll get the same thing out that we put in. So in order to prove this equation, we need to work on an element by element basis. So that's why we choose to invoke extensionality. So you have to prove an equation between two functions. So you invoke extensionality, and now we can see that instead of proving an equation between two functions, somebody gives us a typical input, and we have to show that the outputs agree. So that's easier. It allows us to reason about this input by cases. So I'll then say, well, okay, somebody gives us an mx in. So I'm doing this fancy curly braces round the body of the function notation, which will allow me to pattern match on this thing. So you can see, what are we asked to show? Well, we can't really see what's going on there, but if we do that, you can see it's asking me to show that maybe identity function mx is always, in every case, mx. And the usual rules of how to prove a theorem about a function apply. If it's not, if the equation hasn't simplified to something that's immediately obvious, it's because something has got stuck. We need to figure out why it's stuck in order to get it unstuck. And it's stuck because maybe pattern matches on this argument. So if we pattern match on the same thing, we should be able to get it. We get multiple cases, but in both cases it'll be unstuck. So we look at mx, We get rid of the Unicode. And we see in this case, well, it's giving us some other stuff we don't want to look at, but if we look at it in normal form, we're really just being asked to show that yes x is yes x. So that's clear. And if we look in this case, we're being asked to show that no is the identity function applied to no. Or, in other words, no means no. So we've been able to prove that the laws, well, that this law holds, and the other one's very, very similar. You can see that if the computation succeeds, then we're actually going to do f then g to the value. And if the computation fails, we've had it. So it's the same thing in both places. So how are we doing so far? You see why this definition is the way it is, and whether the proof is all that readable or not. You can see that since all it's doing is applying a function in various places, if you give it the identity function, it'll do nothing. And if you give it a composition of functions, you could have done that one step at a time. Okay. Further down the line, I've got some other bits and pieces. I just want to flash up. Just for familiarity, I define ordinary lists, not length index vectors, just plain old lists with a nil and a cons, and I define this operation which in Haskell you learn to call map, but I call it lowercase list because it is the map operator for lists. If you've got a function on elements, if we've got f as a function on elements, then list f is the corresponding function on lists that does the function to all of the packed up elements recursively. And it shouldn't come as a massive surprise that we can do a proof by induction that if you feed in the identity function and you do the identity function everywhere, that achieves the identity result. And if you map one function across a list and then you map another function across the result, you could have mapped the composition in the first place. So same stuff, just a different pattern of packing up stuff, but the same idea of operating on the packed up stuff. Yeah? And we see that all over the place, right? Here, I've got some random other structure, which I'm calling a bit process, but you can see, same sort of pattern. There's some parameter type x, which represents some notion of, the idea is, this is a process this is modeling processes which can read bits, write bits, and eventually give back a value of this type. So in order to stop, you have to give back a value of that type. So here we're packing up an element. And then there are two other possibilities. You can send a bit by saying what bit to send. Here's the type of bits. I call it 2 because there are 2 bits. But I still call the bits true and false. I call them TT and FF, but I say true and false. So here we've got an element of 2, and then a packed up process for how to carry on after you've sent the bit. And then I've got another constructor called receive, which takes 2 sub-processes, one of which says what to do if the bit you receive is true, and the other one says what to do if the bit you receive is false. But all we're doing is packing up elements of x in some tree-like structure. So it should not come as a surprise that there is a corresponding map operator for these things, which says, well, if you know how to act on the final value, if you've got a process that gives you x's, and you know how to turn x's into y's, you can give back a process that delivers y's instead. Or what do? You take your function that turns x's into y's, and you just traverse the structure looking for x's, turning them into y's. Same pattern, just a more complicated instance of it. You know, nothing to see here in that sense. There's more to come. Because let me try to get at least some of the direction I want to go. I'll grab that far. And then I'll hurriedly delete this, you didn't see it. Because what I want to do next is build another category. So here I'm saying I'm going to work within the category of sets. So let's just have identity and composition for sets. And I'm going to work with, in particular, the maybe functor, but I want to build a very particular category. The objects of this category are going to be sets, much like in the category of sets. But the arrows are not going to be ordinary functions. They're going to be slightly wonky functions. Oh, this should be S. So what's going on here? An arrow from S to T is a function from S to maybe T. Or you can think of that as a function from S to T that might go wrong. You know about exceptions? Yeah? So you can think of this as a function from S to T that's allowed to throw an exception. So what can happen? Either you're lucky, there's no exception, and you actually get back a value in T, or you're unlucky and it throws an exception. And we're going to model that with the no value in maybe T. Everybody happy what the game is, what these arrows are? They're potentially faulty processes. The world is full of them. I mean, whether things are under our control or not, you know, network might go down or whatever, so your read from the network isn't necessarily going to work. No, the world is full of things that might flake out on us at any time. I know, because I'm one of them. And anyway, let's see if we can build the bits and pieces for this sort of arrow. We haven't got everything we need yet, but let's discover what we need. Because it might be nice. If we've got processes that might go wrong, we might like to be able to plug them together in a way that neatly handles the way exceptions do. Right? When your exceptions are allowed, you can write programs and you can throw an exception in any old place, and you know that the exception will always be propagated to the outside. Same sort of thing here. We'd like to be able to combine these processes in a way that stops us needing to worry about managing the exception handling all over the place. So let's see what we need here. To give the identity arrow, we need something which for all t gets us from t to maybe t.
Yes.
And that would be yes. It should also kind of represent boring success. Yeah? We don't have actually got any work to do because we've already got a t. It's very easy to give back exactly that t successfully. And for the composition, we've got to do some plumbing. Look, we've got something, we've got one process that starts with an R and gives us a maybe S. So it could go wrong even before we get our hands on an S. But maybe we'll be lucky and we'll get an S, in which case we can start stage 2. We've got a function that takes an S and maybe gives us a T, so it could go wrong in stage 2. Can we put those two together to make one process that starts with an R, maybe gives us a T? Yeah, so it could go wrong either doing this bit or doing that bit. But since we're allowed to go wrong, it doesn't matter which bit. So we should be able somehow to plug these things together.
Do we just have to pattern match for if those do go wrong?
That's what it's going to come down to. Let's see how far we can get with the components we already have and invent only what we need. Okay, so I better get myself my two functions. I'm going to do it like plumbing. I'm going to plumb arrows together. So rather than working in the type maybe T, I'm going to plumb arrows. We've got operations that put arrows together. So let's see. We've got to build, so it really is, it's like being a plumber. We've got to plumb from R to maybe T. We've got these two bits of pipe. And we've got various things we've got various other bits and pieces. For example, we know that we have composition of functions, which acts like, putting two pipes together if they fit. So we can see that if we're trying to get from R to maybe T, we could certainly start by doing F, and then who knows what afterwards. Yeah? Does this make sense? Just start by doing F. So we attach our pipe F to the input, and we haven't figured out how to get all the way to the output, but we can just leave a gap for that. And now we've got to get from maybe S to maybe T. Now we've got a piece of pipe that goes from S to maybe T. Is there any way we could kind of plumb that onto this maybe S?
Lowercase maybe?
We could use lowercase maybe. So if I say maybe G, what's that? It's a pipe that starts in the right place. Doesn't finish in the right place, but gets us somewhere. So let's stick it in there. Again, composed to heaven knows what. And now we're left needing this operation from maybe T to maybe T. So far we've done nothing that forces us to know anything about maybe. We're going to have to do, this is going to involve doing something important about maybe. Let's just think about the situations that happen. What we're really saying here is, this F might go wrong, and then this maybe manages what happens if it goes wrong. It says, if this has already gone wrong, stay wrong. But if it goes right, deploy stage 2. So then we get a double maybe, which corresponds to something that might go wrong in one of two ways. We'll get a no for the outer maybe if stage 1 goes wrong. The whole thing will be blown already. We'll get a no, a yes for the outer maybe, but a no for the inner maybe if stage 2 goes wrong. Do you see why that is? If F succeeds, we'll get a yes, and then the maybe will propagate that yes. So by here we'll have an outer yes if it works. Yep.
Why can't we not use a normal composition instead of arrows there?
That is normal composition. Yeah, we could indeed I'm making a point for a reason. Because I would have to add some parentheses because I haven't set an associativity, but we could indeed use normal composition. I want to use, in the category of sets, this categorical composition operator is normal composition. Nothing funny going on here. I'm just trying to suggest that maybe there's nothing that specific to the category of sets going on here. So this works pretty much anywhere. So what we're left with is that we need to build a piece of plumbing that says we don't actually care whether it went wrong at stage 1 or whether it went wrong at stage 2. If it went wrong in either stage, it went wrong. If it went right in both stages, it went right. Okay? And this operation is often called join, because it joins 2 layers of maybe into one. We'll call it join maybe. And its type is for all t in set, maybe t to maybe t.
Is that essentially just and?
It's a fancy and. Yeah? To get a success out, we have to have a double success in. Okay? We're going to define it by pattern matching. Okay? So the first pattern match asks, did the first stage work? We get a no in the case where the first stage went wrong. We're dead already. So we're dead. If the first stage worked, we've got ourselves a maybe t that corresponds to what happened in the second stage. So now we can pattern match again. So this yes if no means the first stage worked but the second stage went wrong. So the whole thing went wrong. All right? I should call this a T. In the last case, both stages went right, and we actually got our hands on a T. Then the whole thing went right. So we can give back yes T. So we figured out how to collapse 2 layers of possible wrongness into one by saying if anything goes wrong, it all goes wrong. Yes?
Can you just define the first line and then put an underscore for the second line?
That's an excellent question. Let's find out. Yes, you can. Now, it's one thing you cannot see because the color difference is so subtle it doesn't come out on the projector. But there's a very, very faint background behind this pattern. I can see it on my screen. It's so just off-white. It might have been trendy in the 1980s. What that's telling me is that that this equation won't just hold exactly. It's not the case. It's not the case that join maybe of any x gives no. It's join x of any x that is definitely not yes, yes. So what that's telling you is there will be more pattern matching than this. This equation doesn't just rewrite. So we've seen that in previous times where when we had pattern variables that give us equations that didn't quite rewrite because there was stricter pattern matching going on. Yeah?
I don't know if I missed something, but why don't we just return the empty, like when we had yes empty, why wouldn't we just return empty because empty is of type maybe t, and then we leave the composition function t?
That's also a very sensible question. So the proposal is, see it's telling me I've left some cases out, is that that we do this, and that's perfectly fine. So that's like doing and in a short-circuited style, where if the first thing is true, you just give back the other thing. That's completely fine. Good move, actually. Let's do that. But I just wanted to show that we were really capturing if it goes wrong at either stage, it goes wrong. Yeah?
Would it not be better to write a function that takes in maybe t and then just spits out t, and that way you can use it multiple times over if you have like nested
Let's
maybes?
try. So the proposal is that we write a function that just peels off one layer of maybe. Let's see what happens when we try. And then that will be a good place to stop. In the yes case, we're super lucky. We wanted a t, we've got a t, we're happy. In the no case, we've not got a t, but we're being asked for a t. Where's it going to come from? We can't just lie and pretend we have one when we don't. We know nothing about t.
Could you put a 0 in?
Well, if I had an element of 0, I'd win, but I don't.
Could you say that it's a case that can't happen? Or
But it clearly can happen.
no?
I mean, I clearly can apply on maybe to no. And then I've got to get a magic t from nowhere. So this isn't going to happen, right? Join says, if you want at least one layer of maybe, you can collapse any number of layers that's at least 1 down to 1. But you can't get it all the way down to no layers of maybe. If there's any doubt somewhere in the system, we've got to worry about it. And that's...
Could you do it though, like instead of returning t, you have like that on maybe, like if there is a t, then you apply some function, almost like a conditional?
Now, the sort of thing you could do, you could start saying, well, maybe we should supply something to use as a default or something like that. Then we're actually basically explaining what you would do if you were given a maybe t. That's a possibility, but it's never going to have exactly this type. It's going to have to turn into, we've got to explain somehow what's going to happen if things go wrong. So yeah, that's we can get rid of all but one layer of possibly going wrong, but not the last one, unless we have some external exception handler, which we'll come to. So yeah, let's stop there.